This is about lecture 4, and let us recall what we learned in the lecture 3. And we basically discuss about the ramjet engine, scramjet engine, and also the combined cycle. Under that category, I discuss about two cycles. Basically, one is rocket based combined cycle and other is based on the turbo based combined cycle, but I did not discuss about cycle, rather I talked about how we can combine two engine systems such that we can get a lot of advantages over the each one of them. And later on we looked at the non-chemical rocket engines. Under that category we discuss about the nuclear rocket engines and solar rocket engines and also the electrical rocket engines. Those are only being focused on the basic principles of rocket engines, just to have a bird's eye view of all the rocket propulsive systems and also the air breathing propulsive systems, because it was just an introduction to the whole gamut of the propulsive devices. And today we will look at the what are the tools available for analyzing these propulsive devices, and I will try to cover, rather review the thermodynamics principle which can be useful for analyzing these propulsive devices. And let us start this lecture with a thought process from Uwe Hode, and who says that thermodynamics is a remarkable illustration of ranging power of human intellect, that a principle first detected in connection with clumsy puffing of early steam engines and should be found to apply the whole world and possibly even to the whole cosmic universe. That means, if you look at thermodynamics is really very important subject that encompasses to explain all the processes which will be occurring across the entire universe. And before getting into the tenets of the thermodynamics, let us look at how this aerospace propulsion can be applied or can be based on three subjects. One is thermodynamics, basically the engineering thermodynamics what we will be looking at it, and other is gas dynamics. Keep in mind this gas dynamics is connected to the thermodynamics as well, and so also the combustion, which is very important because we are interested to look at propulsive devices that will be using chemical energy. So, therefore, we will be looking at all these fundamentals related to these three things first, because these tools will be important to analyze the propulsive devices. And now we will be reviewing the thermodynamics, because you have already learnt on several occasions about the basic principles of engineering thermodynamics, but however, for completeness sake I will be starting from the very basic principles. We will ask a question, what do you mean by thermodynamics? If I ask this question, you may be saying, okay, it is related to the heat engines or something like that. But if I look at this terminology or the word thermodynamic, it stems from two words. One is thermi and other is dynamics. Thermi means it is related to the heat, and dynamics means it is related to, you can consider it to be a power. And if you look at what really means the thermodynamics from the engineering sense, is that converting heat into power, and that was the quest with which human being started to strive to convert heat into the power. As a result, the steam engine came into existence by James Watt, who was the pioneer in that. But one has to remember that we may know him, but there are several people who have given their lives to convert this heat into power in the form of heat engine. So, if you look at this, when you talk about these heat engines, then question arises that thermodynamics can be considered as a branch of science that deals with energy and its transformation. And when I say this energy, all of you might be feeling that I know it, we need not to discuss, because we already use it left and right in our day to day life, isn't it? But however, when you try to ask this question, what is energy? Can anybody tell me what is energy? Capacity to do work, or it can cause any change. Suppose I am trying to teach you and I am trying to give my intellectual energy, so that it can be change in your mind, right. So, any change which will be occurring is because of what? Because of energy, right. So, that means energy is everywhere. If you start from even atom, the molecules, in the last lecture we discussed about nuclear energy in the nucleus itself, that energy will be lying. So, everywhere energy is there, right. So, whatever you see, any action, any reaction, anything, whatever is occurring across the whole universe is nothing but manifestation of energy. So, that is a very important. Therefore, I can define energy as an enticing eternal entity that governs all the activities of the whole world. World means entire universe. If you look at the what you call stars, planets, galaxies, and even including our day to day this thing. So, all will be the basically manifestation of energy. Whenever I want to convert the what you call I want to have a thrust power, I need to use chemical energy and convert into the thrust power in aerospace propulsion. Of course, you can use other forms of energy, as we have already discussed, that is your nuclear energy, solar energy, and your what you call electrical energy. You can, but basically what you are doing, you are trying to convert or utilize this energy into the thrust power. So, that is the basic idea of the propulsion. So, whenever you talk about this thermodynamics, then whether can it be connected to the life? And if you recall, the thermodynamic is having three basic concepts or the principle on which it works. One is of course, the energy on which we have already discussed, right. Just now we discussed about energy, and there is another concept known as entropy, which we will be discussing little later on. And whenever you talk about energy and entropy, then we need to talk about the equilibrium, right. That means, these three are connected to each other, and when it is connected and also the governs the principles, particularly the engineering thermodynamics, or we call it as a classical thermodynamics, right. Then now, if I compare this with the life, what are those things? One is your body, other is your mind, and this is the spirit. So, which is very important for sustaining a balanced human life. That means, if you look at these three components must be balanced, and that is the basic objective of a education, to have a balanced life between the body, mind and spirit. When you look at your present or the modern education system, it does not subscribe to those things. That means, it is violating the basic principle of thermodynamics, which is being governed, which is governing all the activities of the world according to me. It is not according to me, but the great scientist Albert Einstein feels that way. He comments that a theory is impressive, the greater the simplicity of its premises is, the more different kind of things it relates, and the more extended is its area of applicability. Therefore, the deep impression the thermodynamics made upon me, it is only the physical theory of universal content which I am convinced that within the frame of work of the applicability of basic concepts, it will be never overthrown. That is the power of the thermodynamics. But let me make you to recall that it is the steam engine which brings or forth this subject as a magnanimous subject that encompass all the processes or all the activities of the entire universe. That means, engineering leads to a science which is now very much extensive in nature. We will be now discussing about various concepts and terminologies involved in the engineering thermodynamics, and most of you will be knowing about those concepts and terminologies. However, we will be reviewing it and relook at it, as it is quite important to recall and also the appreciate the points how it can be applied for propulsive devices. For example, like propulsive devices will be having several components. If you consider a gas turbine engine, having various components like air intake, compressor, combustion chamber, turbine and nozzle. If I take a simple and air intake, then what I need to do if I want to understand what is happening during the flow? For that, I need to concentrate or focus my attention on the air intake component itself and see how it is interacting with the other components or its surrounding. So, therefore, whenever we are talking about a system and trying to carry out engineering thermodynamic analysis, then naturally we will have to consider a system which is nothing but a quantity of the matter or the region in the space bounded by certain closed surface. I took the example of the air intake. In that case, the boundary of the air intake itself will be a closed surface or a surface, right, and which will be identifying the system. So, anything apart from the system, we call it as a surrounding. For example, in this case, this is the system and it is having boundary, and anything outside of the system we call it as a surrounding, and system and surrounding together we call it as a universe. Let me take another example of a hot coffee cup, right. If I take a hot coffee cup, then I will keep in a, let us say, on a table, and I am interested to look at like how it is interacting with surrounding. What will be the surrounding? Because first I need to identify the system, that means its boundary, and when I identify a boundary, I need to look at what I should consider as a boundary. Should I consider the hot coffee, right, if it is full with the brim of the cup, then as a boundary, system boundary, or I can consider as a full cup itself as a system boundary. That depends upon your choice and what you want. But what will be then its surrounding? How will I identify what is its surrounding? Suppose my cup of coffee is here, right, and if you are sitting at far away, can I consider this as a surrounding for this system? Is it? By definition it is, but It cannot be. How? Suppose I will measure the temperature here, which is let us say around 70 degrees Celsius of the hot coffee, and if I measure there, it will be ambient temperature. Even if I will allow these to transfer all the it become cools equilibrium with the surrounding, then the temperature let us say around 5 meter, 6 meter or maybe 5 feet kind of things will not be observed by the thermometer. So, naturally it cannot be its surrounding. So, then how to go about it? It is very simple, that you will have to consider wherever its effect will be. In the case of a hot coffee, it will be within maybe 1 centimeter, there will be change in the temperature or the properties. So, with which the system is interacting. Therefore, we will call the system and surrounding, right. So, it is very important to look at the what is system, what is surrounding. In the book what is given, that anything external to the system will be surrounding, it is not possible, right. So, therefore, it is important to understand this concept, and the system and its surrounding is total is universe. For example, at this moment I am interacting with you, if I consider myself as a system and interacting with surrounding, right, then it will be system and surrounding, all of you people including surrounding will be considered as a my universe, right. System plus surrounding is a universe. Suppose some of you are not listening, will you be a part of surrounding? Certainly no, you are dreaming or doing something else. So, you cannot be a this interaction what we are trying to discuss the thermodynamic subject at this moment, not possible. So, therefore, one has to be worry about identifying a system and surrounding. So, what we need to look at basically boundary. Boundary can be a real or imaginary that separates system from its surrounding, that we have already know. But how many ways we can divide this boundary or we can classify the boundary? There can be a fixed or rigid boundary, there can be movable boundary, right. There can be a dithermal where heat interaction will be taking place between system and surrounding, and there is another boundary where there will not be any heat interaction taking place. We call it as a adiabatic boundary. If I take a system as the gas in a piston and cylinder, what is being shown here, you will find that whenever the system is interacting with the surrounding, maybe we can heat it, so that this the gas will be expanded and piston will move. In this case, the boundary is moving. So, we can call it as a moving boundary, whereas other places like on the other side it will be known as fixed boundary, and if I will insulate it, that means I will not allow any heat to be transferred around this system, then it is basically an adiabatic boundary. So, therefore, like we are aware that there are several kinds of boundary, but in our case of propulsive devices, can we use this, and where we will use and how we will use is a matter of concern for which we will be worried about. So, let us look at how many ways we can classify a thermodynamic system. So, can anybody tell me, because all these things you know, I just want to review it. Can anybody tell me how many ways we can classify the thermodynamic system? What are those?
Open system, closed system and isolated system.
That means, we can classify the thermodynamic system into 3 categories: open system, closed system and isolated system. In case of a closed system, where the mass in the system will be remaining constant, it will not be what you call transferring across the boundary of the surface, right. However, it can allow the energy transfer to take place between the system and surrounding across its boundary, right. and let us consider a simple cylinder or a container which contains certain amount of gas of mass 1 kg, and whenever we are heating it, what will happen? It is having a fixed and rigid boundary. It is not like your balloon. Whenever I push some air, it will be inflated. It is not flexible, it is rigid. So, therefore, what will happen? There will be change in the pressure, because volume is remaining constant. So, and there will be interaction between system and surrounding, because this dashed line which I have shown is your system boundary, and nearby is known as the surrounding. Now, this is known as a control mass system or a closed system. And if I take a piston cylinder example, in this case the mass remaining constant, it is not going out of the system boundary, but there is a heat interaction. Now, if you want to know how we can use this closed system in case of a propulsive devices, can we really use it, or will just because of completeness sake we will be discussing. Let us look at a closed system and how we can identify a boundary, because unless we identify a boundary, we cannot say that which is our system. Both system and surrounding without any boundary will be same. So, let us consider is our earth, which I have shown here. You can say this is the beautiful earth, looks to be quite interesting, and these white color things whatever I have shown is because of what? It is because of precipitation, and there will be lot of mass will be coming and evaporated and going and then recirculated, kind of things happening, even your pollutions and other things. Now, what is happening? The heat is being coming from sun as a solar energy input into the surface, and some of the heat will be going out as I have shown. Now, I am interested to find out, right, what will be the surface temperature and use as a closed system. So, how I will go about it? For example, if I take this as my boundary, that is mean the whole surface of the boundary, can I call it as a closed system? I cannot, because there will be evaporation. The earth contains 70% of water, right. So, therefore, always evaporation will be taking place across the whole globe, because we are interested to global temperature, not as a local, all right. One temperature, what is happening, we are interested to find out. So, naturally, there will be evaporation which will be going and the mass will be going out, and there will be also concentration gradient, therefore, movement will be there, right. There is a atmosphere which will be interaction will be taking place, lot of fluid will be going up and down because of temperature, because of concentration gradient, because of your evaporations, right. So, mass will be going out. Can we use as a control mass system? I cannot. So, therefore, I need to find out which is the right boundary. For that, I can consider this as the red one which I have shown here as a boundary for the closed system. So, therefore, it is very important to identify the proper boundary, otherwise it is very difficult to carry out analysis by considering a closed system or an open system, right. So, therefore, it is important to look at it, to consider it. Let us look at an open system, which we call it as also control volume system. In this case, both the mass and the energy transfer will be taking place across the system boundary. That means, the whenever system is interacting with the surrounding, it will be having transfer of mass and so also the transfer of energy. For example, the same example I am taking, it is from a surface of the sea, and where there will be solar radiation and also terrestrial radiation, evaporation and precipitation, all those things will be taking place, right. If I want to have boundary, I can take this as my system boundary and look at an open system, what is happening, right. And for example, we can take an air intake in case of a gas turbine engine, and where the fluid or the air will be getting into this diffuser or the air intake and going out, there will be some interaction between system, because this dashed line I have taken as a system and rest of the things will be surrounding. So, we need to identify a what to call a system. Now, question arises whether we will go for closed system or whether we will go for an open system, where it will be convenient and how we will choose its system boundary is a matter of concern, and that depends on the individual and also the problem at hand. Now, most of the times in our propulsive devices, we will be using the open system. However, whenever we are using the piston engine, right, then we need to consider the closed system, and some places we may consider, right. So, but in case of an isolated system, neither the mass nor the energy crosses the boundary. Therefore, like there will not be any interaction then, right. But then when will you use it? It is useless to have this kind of isolated system, right. Am I right? Then why it is there? Open system we may understand, closed system we may understand, but why an isolated system? Neither interaction of mass nor the interaction of energy. So, for thermodynamic system is concerned, energy interaction is essential, right. But all you have stated, I want to get the answer from you, right. Let me just tell you briefly that this is being used very much whenever you talk about second law of thermodynamics. Therefore, it is very essential and important, right. So, I do not want to get into that. You please go back and look at your thermodynamics book and how they have handled while analyzing the entropy in a system. So, what I would suggest here that a particular type of system must be identified carefully for thermodynamic analysis of any problem, even in case of propulsive devices, because otherwise everything will be wrong, because unless your initial condition or the identification of boundary is not proper, then your all other things will be fall apart. So, therefore, it is important. Now, whenever you talk about this, the interaction between system and surrounding, naturally we need to look at how the properties of a system is changing, and what do we mean properties, right, that we need to, but it is important. Why? Because a system contains matter, certain amount of matter, and it will be interacting with the system and it will be changing its state during that. So, therefore, we need to understand property. So, if we will ask a question, what do we mean by property, then what it would be? A state of the system or the attributes of the system or characteristics of the system. If I say what is the property of a human being, can anybody tell me, right? We are all worried about property of a system, property of a certain matter, maybe iron, what is the properties, what is the aluminum, what is its properties, but we should know what is the property of a human being. That is very essential than talking about a other material, but we never worry about it, nor education gives this an opportunity to think about it. I would suggest you think about it. So, that means a property will be any observable characteristics of a system. Characteristic means attributes of a system, right, which will be changing and which will be repeatedly you can change. For example, if I say that water is a colorless or odorless liquid, or maybe tasteless liquid, right. Is it water is tasteless or tasteful? Tasteless? That depends upon the salt content, what it is having. Okay. So, therefore, can I call it as these are the properties? We can call it as a property, so far portability of the water is concerned, but however, when we are talking about thermodynamic, we will not be really interested in those properties. So, those will be not of much value, so far thermodynamic analysis is concerned. So, hence, when we will be talking about the properties which will be important for thermodynamics, that we call it as a thermodynamic properties, which must be associated with energy and its transformation, because energy is basically the thermodynamics can be considered as a science of energy and its interaction and its transformations. So, therefore, the properties what will be there is pressure, temperature, volume, mass, density, any other things whatever related to energy and its interaction. So, when you talk about these properties, we can classify it. How can you classify the properties in case of thermodynamic, right? It can be classified into two categories. One is extensive property, other is an intensive properties. What do you mean by extensive property? It will be a property which will be dependent on the size or extent of a system. For example, the mass, volume, right, and total energy and others. See, always I find some of my students are get confused, extensive property, intensive property, right. But if you look at a milkman, right, particularly in India, what he will be doing? He will be mixing maybe with 3 liters of milk, 1 liter of water, it becomes 4 liter of milk. Does he know that extensive property? He is experiencing, he is using, but he does not know that you call it as an extensive property in thermodynamic sense, right. So, let us take an example to appreciate this extensive property. Like we will consider the tank A contains oxygen, mass of 1 kg and volume of 1 meter cube and temperature of 300 Kelvin and pressure of 100 kPa. And I will take another tank which is having same volume, same mass and same properties, and we will add together. What we will get? We will get of course, a volume of 2 meter cube, mass of 2 kg of oxygen and temperature is 300 Kelvin and pressure is 100 kPa, kilopascal, right. So, that means, if you look at temperature and pressure is not changing whenever you are added, or in some cases you will be subtracting. That means, it does not depend on the extent of the system or the size of the system. Therefore, we call it as an intensive property. However, we use also another property known as specific property. For example, specific volume. By definition, specific volume is volume divided by mass, and if you look at volume is an extensive property, mass is also an extensive property. So, the ratio of it is an intensive property, right. So, we will be using that, but I will not be discussing now, as you are all aware of it. So, what do you mean by thermodynamic equilibrium, right? You must be knowing, like, because engineering thermodynamics means always will be dealing with equilibrium systems, right. So, we must understand what do you mean by a system to be in thermodynamic equilibrium, right. So, let us consider a copper block at 70 degrees Celsius and there is another copper block at 30 degrees Celsius, which is having of course a separator. Then we will remove this separator such that both the block will be coming in contact and will allow enough time such that there will be heat transfer from the copper block 1 to the copper block 2, such that it will attain a temperature of 50 degrees Celsius. That means, it has reached a steady state and it has reached a equilibrium, because all are insulated, right. Okay. This block together is in equilibrium, right. There is no change in occurring between these two blocks. So, can we call it as a system to be in thermodynamic equilibrium? Yes, but certainly no. It is basically thermal equilibrium, that means uniform temperature occurring between the system. Then something wrong. Then when we call it as a system to be in thermodynamic equilibrium, when all these equilibrium like thermal equilibrium, mechanical equilibrium, chemical equilibrium and phase equilibrium are being satisfied, are being maintained, then only we call it as a basically thermodynamic equilibrium, right. So, let us consider what do we mean by mechanical equilibrium, where pressure across the system boundary will be 0. For example, if I take a piston cylinder arrangement and this white portion is we will consider as our system, and there is a pressure which is applying and there is external pressure P 2, when P 1 is equal to P 2, we call it is in mechanical equilibrium. And similarly, when we consider there is a oxygen in the container left hand side container which is at 300 Kelvin and 0.1 megapascal, there is another container adjacent to it that is having nitrogen, but at the same temperature and pressure. If I remove this partition and allow it to move slowly, then what will happen? The oxygen will be trying to move to the compartment 1 to the compartment 2, that means from the left hand side to the right hand side, and nitrogen will be moving from right hand side to the left hand side due to what? Due to concentration gradient, that means diffusion process. But if we allow a large amount of time the process to take place, then what will happen in the whole container? It will be all remaining the same. So, therefore, the concentration gradient will be 0 and we call it as a chemical equilibrium. So, let us consider another one like hydrogen, 2 moles of hydrogen reacting with 1 mole of oxygen going to the product of 2 mole of water, and at a particular high temperature, that means some reaction is taking place, otherwise water will not be formed if it is at low temperature. And then if I allow this reaction to take place for quite some time, then we will see that there is no more reaction taking place. It is not true. What is happening that the forward reaction rate is equal to the backward reaction rate, then the system attains the chemical equilibrium. That means, and similarly also phase equilibrium will be taking place during the phase transformation, like example is the evaporation of water, right, or solidifications and other things. That means, we can call a system to be in thermodynamic equilibrium only when equality of temperature exists, equality of pressure, that is mechanical equilibrium, equality of concentration, that is chemical equilibrium, and equality of volume in each phase, that is phase equilibrium. So, let us just try to recall what do we mean by a reversible process. That means, whenever a system and surrounding will be returned back to its initial state, then we call it as a reversible process. So, all reversible process is quasi static, but all quasi static process are not reversible. So, what do you mean by this quasi static? Can anybody tell me? Because this concept you will be knowing, I have not discussed.
So, when reversible process begins very slow.
That means, the gradient which will be there is a very slow, very small, such that the changes will not be occurring, right, or the change will be very infinitesimally small. So, there we call it as a quasi static process, right. For example, if I take a piston cylinder and I will put on the top of the piston some sand grain, and then I will remove a small sand grain from it, and there will be change in the gas as a system pressure and the surrounding, but that change is very small. So, therefore, we call it as a quasi static change. Now, in life what we need? We need to have a quasi static process, so that any changes occurring, it will not affect yourself or others dramatically or drastically. However, changes is inevitable. So, therefore, those are quasi static process, which is essential, but all quasi static process need not to be reversible. And keep in mind that all natural processes are irreversible in nature, but in thermodynamics we will be discussing more about reversible process. So, during certain process some properties remain constant. For example, if it is a temperature remaining constant, we call it an isothermal process. If the pressure will remain constant, we call it an isobaric process. In the volume remains constant, we call it as an isochoric process. And if adiabatic, that means no heat interaction between system surrounding take place, and reversible, right, that means what you call reversible also, then we call it as an isentropic process. So, these processes which we will be using, particularly the isentropic process and isobaric process, which we will be using while analyzing the propulsive devices, right. So, now question arises, what do we mean by temperature? Because without temperature you cannot really think about any heat interactions, right. What do you mean by that? Means it is basically in layman term a measure of hotness or coldness, right, whether how good it is so far, whether it is cold or hot, and it is basically a qualitative description. That means, it will be cold or a warm, or it may be hot, it may be red hot, but is it really we can talk about it? Then it will be a problem, because our senses may be misleading. That depends upon person to person and depends upon the mood of the person also, right, and it will be misleading. Even if you take another example which is not having sense, but man can have a sense to observe. For example, if I take two wooden chair, if I take one wooden chair and one metal chair, right, and will it be kept at the same room, let us say in this AC room, right, having the same temperature almost, but if you go and sit down, you feel, or you put your hand on it, you will feel that one of them is colder. Which one will be colder? Metal will be colder, whereas the wooden will be not that much, right, as compared to this. So, therefore, it will be misleading, right. So, let us consider a example like copper block, which is at 150 degrees Celsius. There is a second copper block at 50 degrees Celsius, and when this partition will be removed and they will come in contact, and there will be heat transfer will be taking place, and it will reach a state at steady state 100 degrees Celsius, that is the average temperature between these two. What is the meaning? Meaning is that two bodies has reached a thermal equilibrium, right, and this concept is being used for measuring the temperature. Remember that whenever you will have fever, we will always use a thermometer, right, and then we will allow for some time to be in contact with the body, right, contact between the body and the thermometer bulb, and then you will measure the temperature. So, that we do routinely, and this if we can, and this is the basis of the thermal equilibrium, is the basis of zeroth law of thermodynamics. Let us consider there is a block A which is in equilibrium with the B, and there is another block which is also in equilibrium with the C. The block C is in equilibrium with the B, right. That means, which is says that the block A is in equilibrium with the block C. That is nothing but zeroth law of thermodynamics. If two bodies are in thermal equilibrium with the third body, they are also in thermal equilibrium with each other. And this is a very common things which is being formalized, right, by the R.H. Fowler in 1931, after the first and second law being proposed, right. Therefore, it is known as zeroth law, and if you look at Galileo, we are knowing, and he had devised thermometer at that time. So, it is not a very thing, but he formalized it. It is a thing which he experienced, but we do not formalize into a law, and this law is the basis for the temperature measurement, as I told just few minutes back. So, what we will now look at is the first law of thermodynamics, and we state that whenever a system undergoes a cyclic change, however the complex cycle may be, the cycle integral of work is equal to cycle integral of heat, right. So, we say that the cycle integral of work is proportional to the cycle integral of heat. Keep in mind that for SI unit, this proportionality constant is equal to 1. Therefore, I have stated directly as that whenever system undergoes a cyclic change, cyclic integral of work is equal to cycle integral of heat. And it was first proposed by the greatest scientist J.P. Joule in 1851, conducting series of experiments. He took some 4 years to conduct several experiments to make this statement in a very systematic manner. And if I write it down in this form, that is cycle integral dq minus cycle integral dw is equal to 0, this work is basically on the system, and if it is on the system there will be always a negative sign, you will be knowing the negative sign convention, and from the system is basically is positive. So, the first law of thermodynamics is generalized of several experimental data generated by J.P. Joule, and also he formulated as a first law of thermodynamics, and there is another person who was also working simultaneously or parallelly along with him, but he is not considered to the proposer of this J.P. First law of thermodynamics. Till that nobody has disproved it, but this law cannot be proved like theorem in mathematics. Maybe that does not mean that nobody will prove this to be wrong. Maybe some of you may try it out, and then like we will have to see. For a closed system, this happens to be dq minus dw is equal to dE, and dE is basically what is the total energy, right, which represent all the stored energy of the system. It can be have two term, one is U, which represent internal energy or the microscopic form of energy, and whereas the kinetic and potential energy are macroscopic form of energy, and there are several other microscopic form of energy as well, which I have not listed here, right. And keep in mind that E is the energy is basically property of the system, whether heat and work are the properties of the system or not. Is it so? Actually, the heat and work are not the property of the system. They are energy in transit. They are not energy in thermodynamic sense, right. So, let us look at how we can really apply this first law of thermodynamics for an open system, because we will be using for the propulsive devices, right, analysis of propulsive devices. So, therefore, we need to learn how we can use this equation or the closed system equations for an open system. So, we will little bit elaborate on this, as we know that control volume can be conceived as an arbitrary region in space bounded by the control surface through which mass can also transfer or flows, and the control surface can be real or it can be imaginary, it can be fixed or movable, right. Let us consider a system which is containing a shaft work, which is having heat interaction, and the what you call some flow is entering into the system, some mass is leaving out of this system, and I have taken this what you call dash line as my system, right. If you look at this is basically imaginary boundary, there is a flow, there is no solid boundary, but it is you are imagining as if it is boundary is there. Now, how to what you call analyze this? For this, what we need to know, we need to understand how much mass is entering, how much mass is going out, and how much mass is being accumulated in the control volume, and that is being expressed in mathematical term, that is dm by dt is equal to m dot C v is equal to summation of m dot I minus summation of m dot t. Keep in mind that this is a general equation, but however, in this case there is only one inlet, one outlet. So, therefore, it will be for this control volume it will be dm by dt is equal to m dot I minus m dot t, right. And this is a basically law of conservation of mass, which is based on common sense, right. It is like your money is flowing, right. How much money you are getting, how much it is you are using, and how much being accumulated, right. So, therefore, it is a very common sense you can apply, and this is known as continuity equation also. We will be using it profusely, and let us look at how we can analyze an open system, particularly applying the first law of thermodynamics. So, what we will do? We will consider the system as a transferring into series of imaginary non-flow processes in succession. That means, you might have taken some videos, right. If you look at the flow, the mass is coming in, mass is going out. Now, if I take a video for a certain time and convert into a snapshots, right, then what will happen? Each moment it will be different, right. So, what will say? We will consider that the initial state, this is a control mass, that means, the mass of this whatever there in this system boundary and plus the mass in the zone in this green color, which is about to enter, and at the mass at the time t plus dt, and this dt is very small, that certain mass is about to leave the control volume, and then this control volume plus this mass together will be considered as a closed system or a non-flow system. That means, this itself is a non-flow system or a closed system, and this is also a closed system, and two closed system in succession, you can call it as an open system, right. Now, during this time, as I told you, mass in region enters CV and certain mass leaves into the region B, right, during this process, and some work is required to mass into and out of the CV, and that we call it as a flow work, which means for maintaining the flow through the control volume, because the flow will be coming in and going out. So, you can imagine as if there is a piston which is pushing the fluid, like which I have shown here, entering into the control volume. Similarly, a piston is moving out, it is sucking the fluid from the out, right. So, if you look at the flow work wise, that means certain amount of pressure will be applied with certain amount of specific volume, which will P into V will be work, and that will be done. It is before entering the thing, and there will be flow which is after entering into the thing, right. It is just about to enter, and this is already entered. And if you look at it, that means on this thing, if I take a piston and then a equilibrium condition, that P A is nothing but your force being applied on this piston. So, therefore, the work done by this imaginary piston, you will keep in mind, this is we are just imagining, actual piston not there, it is a flow work, right, which is being pumped by the either compressor or in a liquid it is a pump kind of thing. So, the work done will be P A, that is a force into the displacement, that will give me P V, it is nothing but work done. So, specific work will be basically work done per unit mass, that is P, and specific volume, it is kilojoule per kg. Work done by the flow at inlet during time, what it will be? W I is equal to P I V I m dot I dt, which we have already seen, right. And work done, and keep in mind that the negative sign is being here, because since is work done on the system, and if you look at as per convention, work done by the system will be the positive. So, work done by the flow at the exit during time dt will be W E P E V E m dot E dt, and total energy of the fluid E total at time t will be then E total t is equal to E t, and that means total energy at t and the energy due to the flow work, that is m dot I E I dt. And you keep in mind that what is this capital? Capital is basically E t is total energy in the control volume at time t, which consists of the internal energy, kinetic energy and potential energy in our case, but however, there might be other forms of macroscopic energy, right. And E t means total specific energy at time t, that is u small u, that is a specific internal energy, and V square by 2 and G z, that is potential energy. So, if you look at what we will do, we will be looking at this energy balance across this system during the time dt and trying to derive an expression for a control volume system. So, for the first law of thermodynamics is concerned. So, similarly, at time t plus dt, it will be E t plus dt, the total energy is equal to the energy in the control volume plus the energy about to leave the control volume, right. So, how much heat is transferred to the CV during this time? That will be the Q dot dt, that means amount of heat per unit time into the dt, that is the energy transfer as a heat to the system. Similarly, how much work to be done by the system. Here I am considering shaft work, there might be other form of work as well, right. It can be electrical work, it can be electromagnetic work, other things which we are not concerned. So, the shaft work into rate into dt will give me the shaft work done by the system, right. So, what we will do? We will now apply this thing to the all those terms in this first law of thermodynamics for a control mass system or a closed system, that is we know dE is equal to dQ minus dW. Keep in mind that dW is having two components, one is shaft work, what will be our interest in propulsive devices, and there is a flow work. So, also we are interested in the flow work because ours is an open system, most of the gas turbine and rocket engine will be considering as an open system. So, if I substitute all these values in that previous equation, I will get this term at the total energy at the exit minus total energy at the inlet is equal to Q dt minus W dot shaft into dt, this is the work done, and this is the flow work which will be the flow work in the exit minus flow work in the inlet into dt. If I divide this equation by dt and when dt tending towards 0, what I will get? I will get E at time t plus dt minus E at time t divided by dt, and these are the terms which will be flow work, right, and this is the energy m dot E and E is the total energy which will be leaving and which will be entering into the control volume, and this is your shaft work and this is the shaft work and this is your heat interaction. So, if I rewrite these equations, I will get dE by dt plus you look at the how much energy is going out, this is the mass flow rate of at the exit into the internal energy, and this is your kinetic energy, this is your potential energy and this is your flow work, right. And similarly, at the exit, and this is the work heat interaction and the work interaction, it can be shaft work, it can be any other work. So, if you look at, we know by definition it is HE is equal to UE plus PVE, right, by definition enthalpy total or the enthalpy is equal to internal energy into the flow work. So, then total energy equation we can write down dE by dt into the m dot in the bracket HE plus V square divided by 2 plus GJD, that is the energy which is going out from the exit of the control volume, and this is the amount of energy entering into it, and this is the heat interaction and the work interaction. This equation we will be using for our analysis of the propulsive devices. So, you should keep this in mind. So, what we will do now, we will be looking at some of the concept. We have discussed about the first law of thermodynamics for both the control volume and control mass system. Now, we look at the second law of thermodynamics. Let us consider a reversible heat engine which I have shown here, and it is absorbing certain amount of heat, that is QH, from a thermal reservoir at temperature TH. It will be very interesting if it can convert all the heat into the work. Then what will be our thermal efficiency? Thermal efficiency will be W net divided by QH, that means 100% efficiency. Actually, it is impossible, and this observation was done by a scientist, and who stated that it is impossible for any device operating in a cycle to absorb heat from a single reservoir and produce an equivalent amount of work. And this was being stated by a Kelvin and also another scientist Planck, therefore, we call it as a Kelvin-Planck statement, and this is known as basically perpetual motion machine, right, kind of things, which will take all the heat and then convert into work. It will be interesting if somebody can do that. And let us look at other way around, that is that reversible heat engine, which will be absorbing the heat Q L, and it is from the lower temperature and transferring to the hot body, which will be at a higher temperature, right. Question arises, is it possible? Actually, it is not possible. That means, no spontaneous flow of heat is possible from cooler body to the hotter body on its own. However, if it is other way around, that means heat can flow very naturally from hot body to the cold body, that we always observe, like we have experienced. So, that is possible, whereas reverse is not possible, and that is known as Clausius statements, which states it is impossible for any device operating in a cycle to produce no effect other than the transfer of heat from a cooler body to the hotter body. These statements, although it is a part of second law of thermodynamics, will it help us to analyze? Certainly, it cannot, only it can give you qualitative way of interpreting the process, whether it is a possible or not. But there comes another statement, which is known as Clausius inequality, which states that whenever a system undergoes a cyclic change, however complex the cycle may be, algebraic sum of all the heat interaction divided by the respective absolute temperature at which heat interactions take place, consider for the entire cycle, is less than equal to 0. And this statement is mathematically can be written as Q divided by temperature over the entire cycle is less than equal to 0, which is known as Clausius inequality. And for a closed system, and when you apply this kind of inequality, Clausius inequality, you can arrive at change in entropy is greater than equal to dq by t, and for reversible process this entropy is equal to change in entropy is equal to dq by t, whereas for irreversible process the change in entropy is always greater than the dq by t. And this is you can apply generally for a closed system, but we will be more interested in an open system. Therefore, we need to derive expression for the open system, which I will not be doing, I will be only talk about little later on. But let us understand first that what do we mean by entropy. Entropy can be viewed as a measure of molecular disorder and randomness. I mean, if you look at a solid which is having a very low entropy, because its randomness will be very low. Why? Because the molecules will not be vibrating only, it will not be just moving apart like a gas, where it will be going wherever it will be around that space. So, therefore, the liquid is having a low entropy and gas is having a higher entropy. And a Boltzmann relation gives you a definition of the entropy, which states that entropy is equal to k into ln P, where k is the Boltzmann constant, the value is given here, and P is the thermodynamic probability. But how we will define it? Because always whenever we are talking about it, we always talk about change in entropy. We may find out from the Clausius inequality change in entropy, but we need to know actual value. For that, we need to look at a pure crystal, and for a pure crystal at temperature 0 Kelvin, entropy will be 0. And that is nothing but your third law of thermodynamics, which states that a pure crystalline substance at absolute 0 temperature is in perfect order and its entropy is 0. What is the meaning of it? That means the molecules will be vibrating, and at temperature 0 Kelvin it will be not vibrating, remaining in the same place. But however, it is a solution or some other thing, you cannot apply this statement. That means entropy cannot be 0 even if the temperature is at 0 Kelvin. So, it is very important to what you call talk about this entropy. It is very useful in our day to day life also as well, because our objective in the life must be to reduce the entropy or minimize the entropy. For example, if I take a load and some people are trying to pull in the one direction, whereas other people are pulling in the other direction, can this the load or the will be moved? Certainly no. This is the similar thing what is happening in our country. Each individual is having their own way of looking at things of selfish interest, so that they are pulling apart each other, not in a directed way. So, therefore, entropy is a very important, and it is important to look at it and handle it. So, disorganized energy does not create much useful effect, no matter how large it is, and that is true for ourselves also. So, let us look at now the second law of thermodynamics for an open system. I have already shown here this kind of system where shaft work and heat interaction taking place, and there is a mass is entering, mass is leaving, and if we apply this Clausius inequality for the control mass in the similar way we have used for the first law of thermodynamics control volume, we can arrive at this expression ds by dt is equal to mass of what you call mass flux at the inlet into entropy into q by t minus the amount of entropy, total entropy, that is mass exit and then entropy what you call at the exit going, and this is known as the Sg is the entropy generation rate during time dt and heat transfer rate during time dt. So, I mean this is the portion what we have covered now. I will just summarize that what we have learned today. We have learned about the various concepts and definitions of system and its surrounding. Then we move into 0th law of thermodynamics, first law of thermodynamics, second law of thermodynamics for both control volume and control mass system. With this, we will stop over here.